Hi, everyone. Okay, let me see. We are about to start a physics project working session, which is actually going to be about metamathematics. And I see that my setup here is not working quite correctly. Let me restart something here. Otherwise, I won't be able to see any comments people are making. Let me see if this works. Yep. Okay. All right. So we have been progressing on metamathematics and attempting to understand metamathematical space, the space of mathematical statements. And we've talked about entailment cones, which start from some small set of axioms and kind of they're like the big bang of mathematics in that case, although we actually think that a better model is this entailment fabric, which starts from all possible initial propositions, but that's okay. But so what I want to understand right now is within the MetaMath database, there are how many theorems roughly? I'm forgetting this now. I think I mentioned that in a post that I did about Euclid. Nick, do you remember?
No, but thousands, tens of thousands, maybe.
Yeah, I sort of thought it was 20,000 or some such other thing. So let's take a look here.
It's what is it? What is it? 44,000.
Here we go. 44,000 theorems, 1,500 definitions. Okay. So the question that I want to ask is, what can we learn from all of these? Okay, what can we learn about the structure of metamathematical space? Or more particularly, what can we learn about the human population of metamathematical space? Now, I believe that, okay, when it comes to, let's take, okay, hold on a second. Let me just write down what we're doing here. This is going to be late in 2021 here. Let's see. Where are we? 2021. This is Metamathematics 53. You know, one day I will have a project that wraps around in the 53 dash MetaMath. Okay, so what I want to explore here is, by the way, whoever's got their microphone not on mute and is making background noise, it would be good if you either muted or didn't background noise. Okay, so the question is, where do human found theorems live in metamathematical space? And that's analogous to saying, you know, where on earth did people build cities and things like that? Even now, CF, where in 3D XYZ space did people build cities on Earth? The answer is clearly they didn't build, so far as we know, a city at the center of the Earth or something. They, you know, they're despite the hollow Earth theory of everything, whatever. I'm being silly, but you know, but there's a very great sort of fact about cities on Earth, which they are all on the surface of the close to sphere. And you know, then there's more detail about why people found, you know, the mouth of a river a good place to build a city. But there's already a lot of information from the fact that they are, you know, there in three-dimensional space. So the question is what the analogous thing is in mathematics. And so first question would be, let's take the case of propositional logic, Boolean algebra. And let's ask the question, you know, which I've asked before, of where are the theorems that people, so what is this? This is What do I have here? Okay. So what did we do here? So this is something where we look at all possible. Why isn't this something that we should be able to get from our entailment cone? Well, this is in a sense an optimized entailment cone. That's all possible statements, and this is the ones that are true, that are derivable from the axioms. Am I making sense?
Yes. Well, shouldn't that be an entailment cone then?
These ones should be.
Yeah.
Possible statements or like possible terms, but not necessarily valid.
Well, this is here. What we've got are syntactically writable down
Yeah.
statements. And here are the ones that are valid. Now,
Right.
this is not what we've been doing. Our entailment cones are much less efficient ways to find these things, right? The
Yes.
entailment cone should give but not as efficiently. So why is that? So the reason is because the entailment cone. Okay, so here's a question. Given that we look at the true statements, there's a question of how big the proofs are, how long the proofs are, and how much those proofs involve intermediate steps that are bigger than the results themselves.
Okay.
And so that's going to tell us, okay, so right now when we build an entailment cone, we don't have a particularly efficient way to do that. It's just splitting out in all directions. Am I making sense?
Yeah.
We could imagine
it's all possible entailments.
Right.
Yeah.
Okay.
But at least those are true, not
Say that
just
again?
valid syntax. At least those are true statements, not just valid terms.
Yeah, I understand. But can we tighten up what we find in, well, I don't know what we call it, the entailment, what should we call it? It's the optimized, it's the part of the entailment cone that we care about. It's not the light cone, it's the place where the spacecraft actually goes, so to speak.
Right.
I don't know, in the entailment target zone.
Retention zone.
What's that?
Retention.
Yeah, okay.
ERZ.
Okay, but so what this is asking is, so ordinary theorem proving, we know the target. We want to find a single path. Okay, So traditional entailment cone, the entailments go out in all directions, like light going out in all directions, as opposed to making, to cross technologies a lot, a phased array or an antenna that goes out only in a particular direction. See what I'm saying? Actually, what we want to, this is the directed entailments is really what we're talking about here. Can we do directed entailments? Not, okay, so the question would then be, this the question is, could we take sort of theorem proving like ideas to tighten up? Okay, imagine we're doing an entailment thing and we simply disallow anything that gets more than one step longer or something. Can we do that? Nick, do we have a way, as we build one of these entailment cones, let's say we start from the axioms of Boolean algebra. Some things we get to are hopeless. Can we identify those? Some will kind of come back. So for example, here, okay, so notice in this picture, I don't know how complicated that picture is, but anyway, so it's a very bad sign, or maybe data 53 is defined in that. This is not exactly the most beautiful piece of code, but essentially what this is looking at, see here, and again, we want your rearranged proof graphs, Nick. Because what I want to see is the analog of this for rearranged proof graphs, where we're asking the question, in order to get to such and such a theorem, did we have to go longer before we went shorter, so to speak? I think what we want to do, let's ask the question. All right, actually, I think we can do this here. Okay. So this is our list of interesting statements. Okay. How big? What are the proofs? Okay, so this is our interesting statements list. Okay, so now, and again, Nick, do you have your proof graph maker? Your thing for taking, so what I want to do is I want to take axiomatic theory. I don't know whether I want the two rule version of that, but Boolean axioms. Okay, there we go. Now, this notation is a bit different, but I want to see what it takes to derive one of these things from here. Okay. And then, because that's a particular path in the entailment cone that gets to that particular theorem. Am I making sense? So,
yeah. So do you want to find the replace path?
Yeah, I think so. But I mean, but yes, that'd be fine. From these axioms to each of these. Make sense?
Yeah.
Okay, so why don't can you tell me how to do that? So for the interestings here, I want to replace, let's see, square gets replaced by overbar, right?
Yeah.
V gets replaced by circle times. And wedge gets replaced
circle plus. Yeah.
Circle plus.
Okay. The other way around.
Wedge
is a conjunction. Conjunction is circle times, no?
No, it's circle plus. Pretty sure.
Okay.
Because it's the timesy thing, where 1 times whatever. Let's see, what are the anybody know how to do this? Let's see. Operators.
No.
Nick is right.
Oh, wedge is conjunction.
Yeah, that would make sense. Conjunction is timesy things.
Yes, no, I know. I'm aware that conjunction is times. I just thought the wedge was the or symbol.
It is. Did we get this
Oh,
wrong?
wait. Like maybe I'm confused. We is like V letter.
No, V is the or symbol. V stands for vel in Latin. It's the or symbol. So which one is right? Is this right?
No,
I mean, I don't think it matters in the end. But go ahead.
it isn't or circle plus and conjunction circle times.
Oh, you're right.
Yeah.
I am confused.
Yeah.
Okay, that's right now.
Mhm.
Oops. Okay, now. Okay, Nick, how do we do this? What should we do here?
If you want, so you want a path.
I want a
Actually,
path.
what I did, so find replace path notebook in the not ready directory.
Okay. Now,
Also, maybe reinstall the Packlet at the top.
this one here.
It's still updating. Yeah, this one.
Is ready to go? Ready to do it? Yes?
Yeah. Yeah.
Okay. All right, now what? Now what do I do?
You do the same. Find replace path takes the same arguments as find equational proof. So if you want to prove something from Boolean axioms, you just
Okay, so then what I say is find replace path of, for example, this thing here, given Boolean axioms. Is that right? Can I just type Boolean axioms like this? Oh, no, I can't. Yeah.
I think, yeah. Oh, wait a minute.
Well, yeah. Can I have the for alls there? Or do I need to state this in terms of arrows and things?
Maybe for rows.
What's that?
For all. Try for all.
For this one?
Yeah, you can test it with find equational proof. If it works, then probably find replace path also.
Okay, that works. Maybe I got something wrong.
So
Go ahead.
if you install the Packlet and then run all the cells.
Okay, so reinstall the Packlet. Okay, now I'm going to rerun these cells.
Yeah, initialization cells.
Or why don't I just rerun everything in the definition section? That's not, why does it have it? It has a bunch of other stuff there. Is that going to be okay?
Oh, it seems to work.
Okay, let's try rerunning. Oh, great. Okay, brilliant. All right, what does all this mean?
So you ignore the tests. So justification is just a sequence of axioms that you use.
Nick, this is
rewrite.
lovely. This is really lovely. Okay, there's the path.
Yeah.
Okay, so now I see. This is a path of the form. This is our kind of primitive entailment cone, not our statement entailment cone, but that's okay. All right, so then what we can do is take those, comma path. Does this work? Yes. Great. Okay, let's see. We could probably want for all A and B. I doubt that will mess it up. No, it doesn't. Oops, for all A, B, and C actually. And then I want to put a hash sign here, and then I want to say /@ the interestings.
Hmm.
I might want to do this in parallel, but I think if I do it in parallel, I might get messed up with the Packlet definitions and things. Do we have the once only? Does somebody remember how to do once only to do a Packlet install on all my parallel machines?
No.
No.
Okay, so we got some problems there. Okay, so let's say length slash that. Wow.
Hmm.
This is rather interesting, actually. Now, which ones are, so some of these are goofy, apparently. Let's take %9 and let's do a map leaf count on the %9 at level 2.
Mhm.
And that's going to show us, hopefully,
Huh.
okay. And that's going to show us the size of the intermediate expressions.
Right.
And then what we want to do here, well, let's do this. Let's just say for now, list line plot. Wow, there are ones that take 700 steps.
Wild.
Mhm.
All right, let's take a look at one of those.
That's
I
interesting.
mean, also these ones are kind of like wobbling
Yeah,
around. That's
yeah,
kind of weird.
yeah.
Okay, so if it really takes 700 steps in the entailment cone, there's not a chance. If that's the minimal length, there's just not a chance of finding that by enumerating the whole entailment cone.
No way. We can't even get to like 4 iterations with most entailment cones.
Right. So the branching, can we compute what the branching ratio of the entailment cone is for these axioms? To know what it takes to go 700 steps. What is the branching ratio? It's roughly, certainly proportional to the number of axioms times, what is it roughly? To get, it's the number of possible substitutions that can be made. So I think it's probably on the order of the number of pattern variables that appear here. Do you agree? Oops, sorry, in the Boolean axioms.
Yeah. Close to it.
Right, so let's go find out. So let's say, okay, so let's do a level of that, comma -1, and let's say length of that. Okay, 30. Approximate the branching ratio for the entailment cone. Okay, so if that's the case, well, it's kind of humorous, right? If that's the case, we're looking at 30 to the 700. Okay. Well, that's
mean,
more
okay.
Eames. That's this question of how big is mathematics compared to physics?
Bigger.
Well, if this is right, it's bigger. If this is right, the featurelessness of metamathematical space has allowed us to go a long way through, there's a lot of reducibility in metamathematical space, which has allowed us to get where we've got to.
Which theorem is that, by the way? Or which two? The ones that require.
Oh, I don't know. Let's take a look. I think we will want to get. Here we go. So this is our interesting list there. So let's take that.
Is it 8 and 9?
It seems like
let's just
the
label them. Can we label them, please? Hold on a second. Hash frame arrow true, plot label arrow #2. And then what we want to do here is a map thread. Those are not complicated theorems.
Well, right. That really attests to the prodigious size of metamathematical space. No, look at those.
No, I think it attests to the hopeless inefficiency of automated theorem proving.
Well, maybe the graph with lemmas is much less complicated than that. Just when you cut eliminate it, it takes you 700 steps.
Okay. Note that this is after cut elimination. Okay, can we see the graph with lemmas?
So you just find the equation of proof as always. You have a proof graph.
No, I know, but I want to see the proof graph that's been turned around so that it goes to this as the destination. Get what I'm
Not yet.
saying?
But it's
You had
pretty
something
close.
very close to that. You had something that was close to it, didn't you?
No, that wasn't really working in general. I think the general way to do it is going to be through this path. It's like first you do it in this, convert it to this path into sequence, right? Into cut-free proof. Then you manipulate it and then use some kind of
believe in
cut
that.
introduction.
No, I don't think so. I think that's not the right way to do it, because I think if you do that, the cut eliminated version is going to be exponentially larger. See what I'm saying? So I just think, yeah, I don't think that's going to work. I think you were close. What was the thing you had before? Where you're simply turning it, you're turning around all the substitutions and co-substitutions, right? You were really close. Yeah.
Yeah, I also thought it's kind of trivial at first, but then I actually tried to do it. No, it's not such it's simple as that, because if you have a lemma, when you use a substitution lemma as what is it? No, when you wanna, if your hypothesis was used as a construct and not as an input, it's not that easy to reverse the direction of it. You kind of have to derive.
What do you mean?
You mean like, I mean that if you have a substitution lemma, for example, you have one equality as an input on which you perform your substitution, and one lemma or axiom as a like kind of rule, right? With some orientation. Yeah. Then you apply it to the input. If your hypothesis was an input, then it's easy. But when it was used as some kind of construct, you have to do it in reverse. To reverse it, it's not so clear how to do it yet.
Okay, well, that's something we need to solve. But let's take a look at these for a second, at the cut eliminated version of this, and also this absolutely weird thing here. Okay, let's actually do the find equational proof version of this. So what we want to do here is just for this, we want to say, didn't you have at least a visual way of changing this? At least a way of changing it to use token event graphs?
Well, we did it for one particular example.
Oh, okay.
Like a
find equational one. Okay, all right, fine. I should have done this one in parallel. Oh, wow. So even with lemmas, those are quite ornate. Well, that's fairly interesting. I mean, so this isn't insanely.
No.
So if we go through here, let's take that graph as an example. Okay, so a factor of 10.
Mhm.
Could be worse. That's really interesting. Okay. So let's now look at what, go ahead.
What about edge count? I think it's more related to the number of steps.
Okay. It's about a factor of 2, which is what we kind of expect, right? Because most vertices have 2 incoming edges, right? Am I right? I mean, other than the initial things, isn't it the case that everything has valence, incoming valence 2?
Yeah. And one outcome.
Yes, which is then counted again in the node that it goes into. All right, so let's just take a little look at what this thing here actually is. Okay, so should we do the 700 one? Let's do that 700 one. A bar. Okay. So now, what the heck can we do with this? We could look at the tree structure of this. How do we get what we want to do is, what is it? Expression graph for each of these.
Well,
Nick, would that work?
expression, yeah, why not?
Yeah.
Well, let's maybe make them tiny. Well, let's see what happens if we just do that. That may be crazy.
Too much rendering.
Yeah. Okay. So let's do %23. Okay, so let's do leaf count slash at %23. And let's do list line plot. Okay, so it gets up to size 200 there. And let's also do depth of %23. My gosh. Well, you know, this is very similar to all these things where, what does this tell us? The fact that this is getting up to size 200, depth 20, that means it's going far out in mathematical space. There are many, many, many terms that are of that kind of size, right?
Okay, I understand.
So what makes us come back to, I mean, that means that there are just oodles and oodles of things out there. And why are we picking? I mean, like any result here. Okay, so let's do this. Let's ask the question: what are the local minima of this thing? What are the wannabe theorems? Do you get what I'm saying?
Nice. Yeah.
Okay, so then what we're finding is, so let's say we take the difference between this and the leaf count Okay, so these are those. Okay, so now this, how do we find the local minimum? How do we find these local minima? Oh, actually, we just want take smallest by. So what we want is take smallest by odd %23, comma, leaf count,
Mhm.
comma, 5, let's say.
It's not going to be necessarily like local minima.
No, I
Maybe
understand.
just
I understand that's
wait.
not local minima. Those are the wannabes, right? So there's the one we actually want. And these are the rather crazy other ones. So the next up wannabe theorem is already something quite ornate that we would say we don't care about. So what does that tell us?
That's interesting. That's interesting.
Yeah, I mean, let's do the same thing for the associativity result.
Okay.
And maybe we should do this again for some other axiom systems in a moment. Okay. Okay, so now let's say take smallest by
Mhm.
sock path leaf count 10. What the heck's that creature? AAA?
A or
What are we trying to
A.
prove this is equal to? Why do we ever get this?
Why not? It's just A.
Yeah, I know, but why does it ever come up? Why? How could it be in the path from this?
Nick, what do you mean, why not?
Well, where is it? Let's find out where it is.
Yeah, I'm not sure why it's there.
How can it appear twice? Oh, because it's got blanks in it. No? Oh, look.
They all, yeah.
It can appear twice. It's not. It's like even though I try to.
Okay,
simplify it a
but
little bit.
also when it says take smallest by. Oh, by the way, our leaf counts are wrong because of the blanks.
Yeah.
Let's fix that actually. Okay, but I don't understand what's going on here. And by the way, another question is how many variables are there as you go down this path? Well, let's get rid of the blanks first of all. So let's say a sock path slash dot p. What are we doing? P underscore pattern colon greater than first of p. Is that correct?
That looks familiar.
Yeah. Okay.
I think I maybe broken something. I wouldn't trust this proof because of this AAA.
Well, in
Maybe
fact,
to
it gives a at the end.
Yeah,
What?
that's weird.
That's wrong.
Well, let's see what the other proof gave at the end.
Oh no.
So this canonicalization.
Wait a second. Oh no, that I guess is right.
That looks right.
Yeah.
So what's wrong with this one?
Well, okay, let me just find out the following thing. So the question is, how many variables are there? Does this ever generate new variables?
It
Do
can.
these, what's that?
Sometimes it can. Not sure about this one. This
Okay,
example.
so let's say length of union of level of hash, comma -1. Well, something went haywire at the end. Something went very wrong at the end there. Okay, so let's go. Let's just do that for every one of these. Okay. Where did we have the results? We have the results on line 9. I don't know what this is, and that worries me. And that might be related to this problem.
Nick, do you know what that is?
Well, messages are fine. It's because find equation of proof has some errors. So I try to mitigate it a little bit. And just
Yeah,
it's
but
like
look,
a warning.
the case that it's talking about looks like it's the associativity case here.
Well, they all look quite associative.
Okay, something went wrong here. I mean, I don't know whether we can find where the stack trace.
No, that's hopeless.
Well, it's
Sorry,
not hopeless. Let's see what proof it was. Look, here it is. It's A equals A times A. Okay, that's where that occurred. I don't know whether they're all in the same thing or whether that's whether.
No, just to.
Yeah, it's A equals A times A is where they're occurring, which is the very first one. Suggesting
just the existence of those. Well, just the existence of those errors doesn't necessarily mean that the proof is going to be wrong.
Okay.
It's just it's harder to reconstruct it, and maybe there's errors. There's still some bugs.
Okay. All right. Okay. All right. Let's get this here. And then let's say length of union, map that onto hash, and map this thing over all theorems. Okay, so there are no new variables generated. In these cases. Which I find a little bit surprising. Okay. So now.
Well, maybe maybe it's better to look at the new variables that actually rewrites what actually rewrites have been done, because I'm canonicalizing my path, right? So each
Oh, I see. I see. At least after canonicalization.
right.
Okay, so let's look at other axiom systems. And in particular, let's look at the axiom system that we looked at the beginning here. See here. Right. So this axiom system okay, so that was an optimal. So let's look at this axiom system here. Okay. And now we're going to look at the optimal path from this to this. I mean, sorry, we've got the optimal path from that to that. Am I making sense? So what we want to do is this thing double equals this thing, right? Or is it the rule? No, it's that thing double equals that thing, correct? So now what I want to say is I want to say find replace path of for all AB this thing here, comma, and then I want to say for all
XY.
Okay, so this path now, let's just get the path here. And we might as well do the pattern removal. Okay, that path is of length 6. Well, that's interesting. How did we find this? This is, wow. Well, it found the optimal path in this case. Nick, what is the way? Hold on here. Okay, what's the way to do this with your modern tools to make the multi-way graph here?
Is it that multi-way nest graph function?
Yeah, it probably is. So what do we want to say? Multi-way rules nest graph. Now, what do I give as arguments? Do I give the pattern rule?
Yeah, rules and initial condition number of steps.
Not clear why I'm starting from that, but anyway, I will start from that. Initial condition, number of steps, let's say 3. Okay, dandy. Right. So now I want to go 5 steps there. And then what I want to say is find shortest path from this to that. What do you know? Okay. So now
little
let's
bit
see this.
different.
It's a little different, right? But what I'm trying to understand is, okay, so let's say ATP path, and let's call this MW path. Okay, so now, this one here, there should be alternatives. So let's take a look there at find path. Right, we know this is of length of percent 49. We know it's of length 6. So we say find path. How does find path work? Can somebody remind me?
6-0.
Like that?
Maybe not.
Let's look at the documentation again.
Exactly.
Maybe it's of length, maybe it thinks that's of length 5.
Yeah, it's how many in between steps.
Okay, this is very cool. Okay, so then these, so let's take this thing here, /dot. Let's just clean the dots up. Okay. All right, so that's percent 53. Let's say position of in percent 52 of percent 53. Okay, dandy. It's there. So let's take a look in percent 52 at map leaf count. What's our figure of merit for what's the winner?
Total is minimum.
Yeah, perhaps. Right. Okay, so in fact, the one found by equational proof is the winner. In this case. Okay. So what we're learning here, so I mean, basically, ATP is good if you already know the theorem you want. Discovering new theorems, e.g. my Boolean algebra axiom, is hard with ATP because you have to know where you're going. I mean, that's why that isn't the obvious thing to do.
Yes.
Now, the way that I did it back 21 years ago or something was to use models. I don't know how that plays into this. That is to find out what is likely to be true with models. Is that something we can do here? We should be able to do that with this set of rules. We should be able to find out likely transformations. Okay, so, general approach might be use models to find plausible theorems. In the same way that you can use hashing to find a plausible theorem. So we should look at that in a minute. and at what that means. Because what we're saying there, let's see. So yeah, what we did was that to use a model, what we're doing is we're picking a model. Let's see, how does this work? For a given model, for all, we're asking, I'm a little confused by this actually. I see, in the case of Boolean algebra, we knew the model because that was the model that was satisfied by a particular set of, so in other words, what we do, okay, so the approach is start from the axioms and find all models consistent with the axioms. Then ask what relations then ask what relations satisfy those models. Does that make sense?
Yes.
So for example, in this case, I think I did this for some cases. Let me look here. As I have this. Here we go, relation to model theory. Okay. So what we want to do, let's make another one of these files. Okay, so we want to take this axiom system here, and we want to say, well, where did I have the nice axiom system? There we go. Find finite models of that axiom system, comma 2, for example. Okay, so there are finite models.
Yes.
And now we want to ask, for a given statement, does it have the same signature? Does it have the same? Yeah, here we go. So this is all ABC. Right now, let me think here. Okay, so here, what we're trying to do, we now want to ask, what's going to be equal to what? Why did I have the function apply finite model? Okay, so I know somewhere, and maybe it's my code 01. Let's see if I have apply finite model. Yes, I do. Okay. So what that's doing is, okay, can we walk through what the different cases are? So, I mean, if I want to find out whether a particular theorem is true for this axiom system, so let's pick, for example, the theorem. Let's pick this theorem here. Okay.
Okay.
So that theorem there should be the case if I say find finite models of that I have exactly the same models.
You do.
You know what I'm saying? Yes. Right. For a theorem to be true in a given axiom system, it is necessary but not sufficient for the theorem to be true in that model, to be true for that model. Okay, so let's understand it in terms of an entailment cone, for example, what this means. Okay, so in this case, if we draw the entailment, okay, so let's say we do this. Doing this just to say graph. What? Why did that not work?
It's because it's not a label, it's a shape. So vertex shape function. Automatic something. I think none doesn't work. Maybe it's working.
Okay. And something's wrong with the graph layout for this multi-way rules nest graph. The default is not right. Right? Something went wrong.
Yeah, the default is where the graph with the root vertex.
But there isn't a root vertex here. Why? But that isn't what we're seeing here. That's not a layered digraph. There's something went wrong with this. See, that does have a root vertex. So, Nick, there's a bug there.
Sure. You just setting the root vertex as your initial one.
I know, but I don't think it's right because
I'm
look,
not
in this case, that was the. I mean, in here, if we say root vertex arrow, okay, something is goofed up here. Possibly because I think we're better off just saying layered digraph without the root vertex, probably. Okay, be this as it may. Let's take this picture here, and now let's label it with the model designations, okay? So every node here is, so each node that can be labeled by, so for example, if I just did this, I'm not going to do the usual blue things because I think they'll be, well, we could do the usual blue things. Whatever, let's do that. Okay, there we go. All right, so each one of those in a given model has a certain value. Do we agree?
Each one of those in a given model has a certain value. Yes.
Okay, so but what's going to happen here is when we try and make an entailment fabric.
That's right.
Then it's going to be colored by its model ID, so to speak.
Yes.
In this case, all of these will be the same. Here, all nodes will have the same model coloring. Is that right? Well, let's use this apply finite model. Let's see how this works. Okay, so let's say it's apply finite model of this. And how would we apply that to these nodes? We'll just say for each node,
Just vertex replace.
oh, I wasn't going to do that. I was just going to color each node. Look, here's what I wanted to do. I wanted to say with G equals this. And now what I want to do is I want to say graph of how do I change these things here to be, you understand what I'm doing? I want, well, actually we could just say vertex shape function arrow automatic.
Yeah.
And then we could just have vertex labels here, graph G, vertex labels, arrow, apply finite models, hash goes to apply finite models of hash slash at vertex list of G. Am I right?
Yeah, I would have done it with just vertex replace. We replace each vertex with some kind of style vertex.
Right, what the hell happened here? Apply finite model. Okay, let's take a look. Oh, we need to make a hash code of that. We need to do flatten. Brilliant. Okay, that's exactly what we would expect. Right? Now, is that true for any model? Let's pick a model that isn't a model of the axioms.
Okay.
Okay, so 1110
That's right.
doesn't appear to be a model of the axioms.
Oh, this will be interesting. What happens now?
Different.
The model will say. Okay, beautiful, 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 beautiful. Now, actually, what I want to do here, let's see, the axioms are always thing to thing. So that's what we're constraining to get this model. So let's just go through and just for the hell of it, let's just do all of them. How many are there?
16.
What's that? 16. Yeah, okay, fine. So let's just do this with a labeled of flatten of hash from digits comma 2. And let's go, let's see, how do we get this? Is it tuples? I don't know, that's 0, 1, 1, 0, doesn't matter. 1, 0, 2, 2, is that what gives it to us? Yes. What happened there? Oh, silly me. What did I get wrong here? All right, so let's look at these. So some of these, which should be precisely 0, 1, 5, 7, 10, 15.
Zero looks fine.
No, look at that. You see there's 48
Oh,
showing up
darn,
there.
darn.
Because no, that's exactly right. 0, 1, 5. So these ones, like these ones
Oh,
where
I
it
see.
isn't
Yeah,
true,
yeah, I get it.
right, have different models.
Right. I get it. Okay.
So to what extent can we think about these models? I don't know whether they're like reference frames. What the heck are these models like? How should we think about this? So,
well, let's say we thought of it in terms of reference frame. What does it mean if you don't have reference frame 0, 1, 5, 7, 10, or 15? Like, what if you have 13, for instance? And you have
yeah.
this
Right.
2
So, I
or
mean,
7.
what we've tried to do. Okay. So what we're doing here, if we find a model.
Yes.
So if we find a model, then every entailment cone is painted the same.
Mm-hmm.
Right. Every node in the entailment cone is painted the same in that case.
But if we don't,
yeah, that's different. But now let's look at the case of an entailment fabric. Okay.
yes.
So let's look at our friendly entailment fabrics. Let's find one here. Okay, so I have one here. It's based on string apply, which I don't think is really what we want. So let's make an entailment fabric that's not based on string apply.
Mm-hmm.
Okay, Nick, how do we do this? What we want to do are make little entailment cones. Okay, so actually this shouldn't be too hard. Yeah, what we want to do here is this is our way of making entailment cones. Okay, this thing here. So what we want to do is for each what are we trying to do here? You know what's confusing is that we've got a cumulative. Okay, what we have been looking at in the entailment cones, in the entailment fabric, is a cumulative is how we build up a cumulative entailment cones. Am I making sense?
Right.
Okay, so what we want here is, okay, so we want to build a cumulative entailment cones Well, I wonder whether that's the only thing we can do, because we could also imagine maybe we can build an entailment fabric more straightforwardly. Okay, so the question is, we want to build a cumulative entailment cones from different axioms and see how they overlap. Okay, for any given axiom, yeah, this is going to be nice. This is going to be nice because what we can do is, for any given axiom will have certain models.
And certain entailment cone.
Yes. It will also have certain models and certain entailment and certain theorems that are true. Okay, so the entailment fabric knits the cones together by their common theorems. Right?
Right.
And so they could also be knitted together by their common models. As in, when the models agree, and that is because the model is a hash code, which will do more knitting than the common theorem case, right?
Well,
Because a common theorem, what's that?
How do you knit it by the common model? It's like
We say
you call it. So each axiom is like a different.
Oh, you're right. Right. They can also
Cone.
okay, you're right. Okay, we should color. Okay, we can color by their common models. And then what we should get which will make some kind of tabby cat, where the thing won't all be the same color. It would only be the same color. I think we have to do it and see what it does.
Yeah.
By their values under a model. Okay, so let's do it.
Mm-hmm.
Okay, so first we have to make the entailment fabric for a expression rewrite system. Okay. Now, by the way, here, see, I'm a little bit confused because in this case here, no, I guess this is right. So this is asking for which models so every path in here, every connection in here. Okay, so if we did the accumulative version of this,
Okay.
okay, in the accumulative version, in the accumulative entailment cone, everything let's see, how does this work? Okay, we can ask what, yeah, this is the right way to do it, what the model spectrum is for each node. Okay. Okay, so can we do the accumulative case here?
It's going to be the same as, like, it's the same spectrum as for axioms. So given your initial condition, your axioms, it's just going to retain the spectrum for each node.
You're right. You're right. You're right. You're right. You can ask what the model spectrum is, and entailment will preserve Nick, is that obviously correct? In the case where the model doesn't, oh yeah, right, because these are the cases where it does work out. Okay, let's just try it for one case,
Yeah.
please. Just
Yes.
try it, just to make sure we actually know what we're talking about.
Yes, please.
So what we want is the accumulative version. So we've got this thing here, and how do we make the accumulative version? I believe, and Nick, remind us, I believe we use
The token event graph.
token event substitution graph.
Yeah. More.
That's nice. If I rerun this, this should give a better result. Hold on. Okay. All right. So that's what we get. So now each of these, we then want to make the model spectrum for, right?
Okay, great.
And Nick, I think you'll find finite models as a way of just giving the spectrum, just the signatures. Do you remember what that is? Can you look it up?
Yeah, sure. Just indices.
Okay.
Yeah.
Do you think I have to remove the blanks to make finite models work? I probably do.
Yeah, probably. Most probably.
Oh, I forgot the indices. Quotes indices. What happened here? Oh, finite models probably needs, in addition to this, it needs slash dot two-way rule
Equal.
goes to equal. Splaffle.
True.
I bet your finite
Event.
model deals with that.
There's also
Oh, yeah.
event,
Yeah, okay.
except event.
I was just going to do vertex list there.
12. Blank 12.
Oh, we didn't do the vertex shape function. Oh, come on. What's happening there? Okay, so let's see what happens if I say find finite models of this thing, comma 2, comma indices. Well, let's just flatten that just in case there's some actually weird thing. I'm going to do something crazy just because in case there's some weird thing about this. What the heck? Okay, what happened here?
Is it like can you put everything in parentheses, like whole map operation? Vertex label arrow in parentheses.
Oh gosh,
Yeah.
did I screw that up? I screwed that up. Brilliant. Okay, something is wrong here. Or at least we didn't understand something, because this is showing a different model spectrum for these different theorems.
Yes. Yes, I see that. It's interesting.
Okay, so let's try to understand that for a second. Okay,
Yeah.
so let's look at the theorem. Okay, that's probably the trivial true statement here.
Mhm.
Okay, but so there appear to be models like 14 of this thing that doesn't exist for this thing. Okay, so let's take this. Okay, so now here, I don't know what we do with the true thing. What does your find whatchamajigamy do with true?
Not sure. Maybe just ignore it. Because treat it as a symbol. Yeah.
Okay.
Maybe somehow pass in an unavaluated form.
Yeah, we can do that, but I'm trying to understand this now, first of all. So that's saying that in this case here, the model 1110 is a model for that entailed thing,
Yes.
but not a model for the initial one.
Right.
Okay, thinking for a second. So
Yes.
one way, let's do this at 2 steps. I just want to see what it looks like.
Two.
Yeah, I'm just thinking for a second. Yeah, okay.
Interesting.
Okay, what's the right way to do this? We can get a number. This is a number. How do we make this number? This is a number where up to 2 to the 16, right?
Yeah.
How do we make that number? We want those bits. So we have a sparse array. What do? We say normal of sparse array of hash arrow 1 mapped onto the thing.
Maybe just fold bit set, but it's okay.
That's a good idea too. Comma. I don't use bit set. What does bit set do now? I'm sure I remember vaguely designing this creature.
So we start with 0. Just
So by the way, we should give this as an example. We should give that fold as an example. If you can send that in, it's a good idea.
okay. I have no idea where to send it.
I don't know either.
Bugs and just suggestion.
I would just send it to bugs. Okay, so in the integer end, so what we want to say is fold a bit set of, oh, it's
Just bit set.
Yeah, it's just bit set, isn't it? This is a nice example. 0, comma, and then let's say let me have a good example. Well, we can just do, okay, so let's put that in a fold a bit set. And
Okay.
we live dangerously here. I'm just inserting that. Lovely.
All right. Well,
Actually, I want to make a picture without the bit set, just so that we see what that looks like as well. All right, so what that's saying is this, Actually, another thing we could do is illustrate these with black and white squares.
Yeah, that's what I was thinking. Right.
All right, let's do that as well. Here, instead of this, what we want is an array plot of, can we do the sparse array trick or should we do something different? Let's do sparse array, hash arrow 1, ampersand slash at that. And I have to say 1 plus this in order to avoid sparse array getting confuzzled. I need to have a list of normal of that. Mesh arrow true, image size arrow 60. Well, not super obvious what's going on, but a little bit more obvious because there we've got ones. Actually, what we really want to do is not list of that, but what we want to say is partition comma 4. And we want to say comma 20. Okay.
Yeah, dude. Okay.
So that's showing us the signature of what models
Oh, this is
are,
nice.
are. Okay, so what's happening is the models may be bigger or smaller, basically. The set of allowed models may be bigger or smaller. Go ahead.
They can be smaller than our initial axiom, right? It starts with just those two black dots. Just
no, it
first
doesn't.
2 bits.
There it is. No, there it is.
Because we had one, Nick, that was just 0, 1, for instance, right? And that's smaller than the initial condition.
Yeah.
But can we explain this? Is this why we have entailment fabrics and not just cones? Because even cones themselves.
No, I don't think so. I think that this is. Okay, hold on. What this is saying is, this is very weird.
Yes.
That this has fewer models I am confused. Okay, I want to try something, which is
what specific aspect of this is confusing to you?
I would have expected what we saw up here. That is an entailment cone. No, what I would have expected is that there will be theorems. What I expected. There would be theorems that allow more models than the initial axioms. It is surprising that there are theorems
What, that allow less?
yeah. Okay, so let's try to understand that. Why would there be a theorem that is implied and entailed
Yes,
by this,
yes.
but which allows fewer models?
Look at this.
Because it doesn't entail the other way around. No. Go ahead, Nick, what were you going to say?
No, we just wanted to see this particular example. Like, just take one axiom and this one where it.
Yeah, all right, okay, fine. Silly us. The issue is those are the trues.
All right. The ones that we
So in
should.
fact, what we want to
filter out.
do is, I think we want to force find finite models. Look, find finite models is going to get confused if it doesn't have two variables. So let's actually force it to have two variables. And let's see what it does with two variables. Find, right, it can be given a number of variables, right? The number of variables to use, if I'm not mistaken. Am I right?
Yes.
Well, variables is not an output of the finite models. You just need to look to have a small circle there.
No, I understand that, but I'm asking, how do we say how many? But how do we tell it what operators to look for, or what? Do you get what I'm saying?
It should have, the operator should be somewhere in the formula. So your true just has to be enumerated A equals A. Or something.
No, I think it needs to be.
Well, yeah.
No, but it's not going to have a
to,
circle in it. We just get rid of the trues, I think.
No, I think you just have to extract a specific key from the output of the finite models for the small circle. If it doesn't exist, you just ignore it.
Okay. I think, let me see, if I just say indices here. Okay, what are you suggesting? That we
select key exists small circle. And then you use
in what? In the thing where we have.
Yeah.
No, but that's not what we need for this full thing. We need it for some particular key in that. Do you get what I'm saying?
You need small circle key because we are looking for the models.
Look at these. Look at these. You got to get rid of
Right.
those. So what do you think we do here?
What do you mean get rid of those? You just select from this association those that have small circle as a key inside of it.
Tell me how to do
So
it.
just select key exists small circle.
How can that be right?
And for example, if you just
because you say that key exists Q is being applied to the right-hand side.
Yeah, right.
Okay, and then what we do for that
keys
is we just say keys of that.
Yeah.
But now what happens if we've got a true there?
That's going to be an empty list.
So what's that going to show up as here? That's going to show up as white here, which is not what we want. We actually want it to show up as black.
Yeah, but yeah, we need to just treat this empty list somehow differently.
Right.
It's
Okay.
like
All right. Okay.
absence
Fine.
of
We'll do
models.
that. We'll do that. But hold on 1 second. Okay. All right. So it's not it's a presence of all models. Every model works. Okay. So here, what we want to do is we want to say in this, find finite models. 2, instead of indices, we want to just have nothing there. And then we want to say keys of select of this thing, comma, what did I get wrong here? Help.
Bracket hell. You should use operator forms more.
I should use operator forms more. Okay, so now what we want to do here okay, so this if this here is the null list, if hash triple equals null thing, throw, we're going to get that, otherwise hash, apply that to this flattened thing, okay? And then what we want to do is catch here that throw, and what we want to throw there is simply array 1 ampersand 4x4, correct?
Yeah.
Okay, let's try this now.
There's still some weird, just 2 bits model. Oh, it's the old one.
That's the old one. Okay, so the claim here this is good. Nothing ever gets smaller.
Yeah.
Right?
Now it's reasonable.
Yeah, so this is showing okay, so let's go back here. Actually, let's replace this with the one that let's just replace this before we forget what's going on. Okay, so now let's go back here. And many things are the same. Except that here, instead of that throw, we want to say range 0.15. And instead of all this, get rid of all of that. What do I have to do now? Help, where am I? Okay, I don't want the array, but I just want frame there. That didn't look right.
You have mesh and image size. That's for framed.
Okay, great. That looks good. Okay, in this case here is the analog of that, but it's framed to bit set 0. Okay, for what it's worth. So I believe that those numbers will be non-decreasing. Right, those numbers have to be non-decreasing. Yes. Right?
They should be. And they appear to be. Yes.
Okay. Okay. So that's telling us that one thing we can deduce in the sea of all possible expressions, those that appear in the entailment cone. So, okay. So in this case, in the sea of all possible expressions, those that appear in the entailment cone must have the same model signature. So this, in fact, this is some. And so what we should be able to see there is if we look at all possible expressions. Yeah, this is the entailment fabric story. Those that appear.
Yes. Yes.
Yeah,
Yes,
right,
yes.
right. So they can't be in the same entailment cone. So let's see, how would we draw this? What we want
That's
to show.
right. Exactly. Good. Okay.
Right. If two expressions are in the same entailment cone, I've written the word code too many times. There must be they must have the same signature with respect to a model of a particular size. Okay, so let's see that. let's try to pick up the expressions So, okay, so in this case, we can make an entailment fabric by looking at all possible initial
Mhm.
expressions.
Yes.
Right, so here, okay, so this would give us all possible initial expressions. We'll find a certain set of connected components. That's what we should look for here.
Okay. Yep.
Now, unfortunately, we would have to prune it by the size of the expression. So let's do this as an example. So let's find, okay, well, how do we get all possible expressions of size of 3 leaves or something? How do we do that? We say groupings. Who knows how to do that? Nick, can you figure this out? Be with us.
You just say,
Tuples
I
AB.
don't know,
What?
isn't just groupings? What you
No,
want?
because you have to have the different expressions of different sizes, right?
Okay.
Okay, so here we need tuples, we need table of tuples up to size n. N goes up to 3. Then we need to say flatten of that and union of flatten of that. And then we say union of flatten of that, comma, small circle, arrow 2. How can there only be 2 of those? What are we doing wrong here? Tuples.
We flatten to some level.
Oh, stupid. It's the catenate bug.
There you go.
Okay, so there are those things, okay?
Mhm.
So now for each of those, we can build like the 2-level graph,
Okay.
okay? And then we're going to do, and then from that, we want graph union. Does graph union take a list?
No.
Okay, so those are the distinct entailment cones. It's a little bit suspicious that there are that number of, let's just see what happens if we say, a little bit complicated here. Well, let's see how many connected components there are. Do we want connected or weakly connected? I think we want weakly connected.
Weakly.
That is not a good sign because I believe there are 16 of these. There are not, there are 22. Okay, great. So what this tells us is that we have some things. So this goes up to leaf count. This goes up to a certain leaf count, and many of these will be splitting out in directions that have giant leaf counts,
Sure.
right? So we could prune these down to show us only the leaf counts we want, and then we could look at their signatures. And what will happen is,
Yes.
in this picture,
Yes.
there will be things that have the same signature, but they are not connected by entailment. You see what I'm saying?
Yeah.
So in a model, they will be the same, but they're not actually provably the same. So do you think we should try pruning this down? Let's try and prune it down for a certain leaf count. Okay, so how do we prune that graph to have a certain leaf count? We do a vertex delete, presumably. Do you think that's the right thing to do?
Yeah.
Okay, so let's say vertex delete. Can we do that for all vertex delete in G of select vertex list of G leaf count?
You can just use pattern for vertex delete.
Here, this will work. This is leaf count greater than 5, let's say. So there are a lot of singletons there. Okay, so let's say we go up to 7. Okay, so these are, so now we can ask which of these entailment kinds. We're basically, it's like one of those extrudable 3D printing things. We're basically extruding from the sea of expressions. We are gradually extruding. Okay, so in fact, what we want to do here, let's just see what happens if we say 3 here. Oops.
Same.
Appears to be the same. All right, let's see what happens if we we need to go up further here. This might take a while. Oh, this should be run in parallel. Okay, so there are lots of singletons there.
Interesting.
That's because we've got to bigger things. Tuples, comma 4 means we have things up to leaf count 4 there. And we're allowing up to leaf count 7. This is our little tiny entailment fabric. This is our threads are not going very far. Each individual thread doesn't go very far here.
Right.
No, it's also leaf count is not counting the actual symbols there.
Yes, it is. Yes, it is.
It's like, well, for example, if you just have leaf count of a plus b, it's going to be 3, not 2.
You are right. Okay, so what you're saying is what we should be counting is not this, but length of level -1. Is that right?
Something like that, yeah.
Let's do that greater than 5, let's say. Actually, really greater than 4 is the honest thing to do. And we get the same result. Okay, so these are the entailment cones that are starting to come out. We start from all possible initial conditions and we say which things are connected, or
Yes.
alternatively, we start from an axiom system and we say which new things are entailed from that.
That's right.
And in this case, right, so the thing we would want to do here is to make an entailment fabric where we start with all possible axiom systems. And we ask, what common theorems do you get?
Mhm.
And what common model painting do you
Colorings. Yes. Right.
get? So, okay, so we say start from what common theorems they make. I think this is what we said. No, it's not common theorems, actually. Are these two-way? These are ultimately two-way, aren't they?
Yeah.
Is that right? Sure doesn't look two-way here.
Oh, it doesn't look because you start with the what? Like symbols. And then they get canonicalized. And it's
Oh,
differently named
God.
variables.
Oh, God.
Just canonicalize your initial rule.
I
think
know.
that's the right thing to do.
I wonder whether that's an issue in other places of things I've already written. Somebody should check that. Okay. Okay, let's canonicalize this. Okay, what is your, oops, what just happened there? What is your canonicalizer?
Lowercase canonicalized button.
Okay. That didn't make a difference. Something confusing is going on here. Okay, we need to look at this, but not right now. Okay, let's keep going. Okay, so what we have here.
I know you can go back from trivial thing. Exactly.
Tell it again.
I think
What?
if you have A equals A, I'm
What do you
not sure.
think?
But I'm gonna look at it.
Yeah, okay.
Not sure.
Okay. So okay, so back to this. So what we want to do is say, how are things connected? So in this case, we are saying, how are things connected by entailment? And then how are they connected in a model? Okay, so let's take a look at this. And what we want to do here is, instead of doing this, we want to paint these with a model.
Okay. Yes. Good.
Okay.
Mhm.
Okay, so now we want to say, okay, this is the entailment / proof structure, is this here. Entail as opposed to entrails. Okay, that's the entailed thing. And actually, we might as well not even bother with the vertex labels here.
Agreed. Okay. Yep.
Okay, now for these, what we want to do is, the first thing we want to do is just color this with the, for a particular model. Okay, so let's do it with these models that we had up here. Right, it's this thing here, I think. Color this for each model. So what we want is the entail. If I'm not mistaken, we just say, I think we just say G equals entail there. Okay. All right, so now in the cases where in the cases where this is a model. Okay, so in 2, this isn't a model. And therefore, there are things that would be some of the entailments are not correctly represented.
Mhm.
It's found a counterexample. It's like what it's doing, right?
Yes,
When it
that's what,
finds the lower number model, it's like finding a counterexample.
to the model.
Yeah, well,
Yeah, to the model.
Right, so what this is showing is, okay, so in a model, wait a second. If the proofs all work, everything that's connected by a proof must agree.
Model
wait a minute.
wise.
In a correct model,
Mhm.
let's see, how does this work? How does this work? In a correct model, everything connected by proof must agree.
Agree model wise.
Yes.
Yes.
In an incorrect model,
There's disagreement model-wise.
right?
And
So
does that mean it's variegated color-wise as well? Whereas if it agrees, it's basically monochrome. Is that right?
yeah, I think that's right.
Yeah, okay.
Okay, but it's going to be a little different for the accumulative case. That's what happens in this case. So as a theorem finding procedure, see, I think there are going to be cases where this is the thing I'm confused by. Oh, yes. Yes. I mean, the point is what we're not seeing here. Yes, this is the prime mistake. We should be doing this on a different case. Okay. You'll see.
Okay.
You'll see what
Okay.
happens. You'll see what happens. We want to do it on this case here. Well, let's do it for, wait, hold on a second. That's for 2, 3. Okay. This is going to be more interesting. Okay. Now, what are valid models? Because
Those look okay.
no, but there will be singletons.
no.
Okay, so we have to remember what the valid models are. Okay, so the valid models.
What? 0, 1, 5, 7, 10, 15.
Yeah, okay, so let's go down here. Okay, now notice that in this case, there are 3s and there are 15s. Okay, so in the superval possible expressions, not all will be connected ever. But we don't actually know whether the 3s will connect to the 3s. See what I'm saying? Those are colored the same by the model, but they may not be proof connected. Do you get what I'm saying?
But they are like candidates for connecting, the best candidates.
Yes. But here, why does this give? Yeah, most of these cases, we're not seeing all of them being equal. This may be a trivial case. Right, so these are candidates for connection. So the way we should draw this is, if we drew it let's see, we could draw it with all the level 1 things. Hold on. What we're saying is there are level 1 things that never connect. So this, for example, let's take this case, which is the second case here, right? This is the case of model number 1. And then we can ask the question, will anything ever connect? Will those things ever connect further?
That's a good question. Right.
Okay. So this is now, and further connection simply, we right. In this case, we can go, okay, hold on, because the obvious thing to do is this case here. And now, what is that one? That one is sub 2, I think. That's AKA model number 1 is this. All right, hold on. Nope, I don't need that. Just need this. And this is this here. And then what I need is this here. Agog. All right, let's try that. Okay, that's that. All right, now what I want to do is I want to say table with that. Are there fewer connected components? I'm not understanding. Why are there singletons here when there weren't singletons here? Do you think that case t equals 0 will work? That should be a bunch of singletons. Oh gosh, it doesn't work. But you understand that that should be okay. If I just get rid of this, how do I make the graph? I just want those to be individual nodes. Right, I think I just get rid of the graph union. I get rid of that. Is that right? How do I make a graph where it's just a bunch of vertices?
Empty list for
That's the
edges.
second argument. I shouldn't have t goes from 0 to 3. I should just have t equals 0. Okay, so I claim Why the heck is the number of nodes different? See, how many nodes does that have? Oh. It's because this thing here says greater than 4. And that thing there should really not be any bigger than, see what I'm saying? This thing here, this is the number of leaves. That should go up to 4.
4. Yeah, okay.
And then this is greater than 4.
Okay, let's see.
Yeah. Okay, so what should happen is that those should gradually merge into each other. I think we may have horribly lost people who are on our live stream. I had a few questions here about it's really dull. So for this particular axiom system and this particular, so if we just compute here graph connected components, that's probably not going to change. Is there a way of counting the number of connected components?
Not sure.
You know, I should use operator forms more. You're right. Okay. So what could be happening here, and we need an example where it does happen, is where these things are gradually congealing more.
Yeah, right.
And wait a minute, this, does it matter which of these? No, I see. That's a property. That's a proof theoretic property. How much merging there will be. I mean, we could try. I wonder what would happen if we were trying. I have a feeling it will just blow everything up to do this, but I think maybe we could just try the smaller case, see whether that does anything. N to 3, this case to 3. Boring. All right, let's try the bigger case. Okay, 4. Let's only go up to 2 because I don't think anything much is going to happen after that. Oh, we did 4, so we need to do 5 now.
By the way, don't you have to run like transitive closure on the graph? Because when you're deleting the vertex of the higher leaf count, you would delete all the connections.
That's a good point. So you're saying I should be running transitive closure before I run the vertex delete.
Yeah. Because even there is a connection for some kind of vertex with a higher leaf count, you just delete it and you delete it together with the connection.
Okay, where did I start doing these vertex deletes? Up here. Oh ho ho. Well done, Nick. I think you're right. Let's just think about it for a second. Is there any way that you might not be right about this? I think you're right. Okay, note that this is using transitive closure. So each edge might be a multi-stop edge, so to speak. See what I'm saying? It could be that it actually goes through that has a waypoint with larger leaf count. Do you agree, Nick? Do you agree with that claim?
Yeah, right.
Okay, so now if we do the corresponding thing, it was just another case of that. Okay, where are we doing the vertex delete again? These didn't have vertex delete. Let's see, this is the case where we really want to do the transitive closure, I think. Oh, that's nice. The graph's changed. Oh, that's very nice. Look at that.
Mhm.
What do you know? These things, okay, so what's happening in this graph then? Oh, this is beautiful. Things that were separated nodes
Yes.
combine, but only when, well, let's see whether we've got the better version of it here down. Did we do this? They only combine when they have the same model, when they have the same ID under this model.
Good. Well, that
But what we
sounds
have
right.
to check,
Yes.
what we have to check is that if this is with a correct model.
Okay. We should try it with the,
With an incorrect model,
yes.
so that was model number 1, for example.
Mhm. We do 2, 3, 4, 6, 8, 9, 1, 12. Any of those.
What's happening with this? Why are these getting on top of each other? Well, who knows? Okay, which one are you proposing?
2, 3. I mean, what the valid models were 1, 0,
All right,
5,
okay,
7,
so
10.
let's do an invalid model. It's just 1, 0 there, right? Well, look at that. Okay, so in an invalid model, there are things connected.
With multiple colors.
Right, so things combine, but we can't tell what's going to combine from the coloring because it's wrong.
That's right. Yep.
Okay, so this is our example. So this is where we can tell what could combine. So we really want to start off with this thing here. Is there a better way to draw this? Well, this is terrible. Okay, so then this is progressively combining. Okay, what happened to our 5151 guy here? Oh, here it is. It's now a whole nest of 51s. Is it area 51 or is that area something else? Can't remember. Area, the one in the UFO one. I can't
Yes,
remember.
yes.
The, there's a whole nest of 51s there.
Yes.
Okay. So, I'm not going to make any jokes about hyper aliens or anything.
Well, not until we answer some live stream questions, right?
Yes. Okay. Okay. So here's. So okay. So this is the case where we're starting from all possible. We're making an entailment fabric, starting from all possible initial conditions. And each one of these things is not a different axiom system. This is the non-axiom system version. This is things which are equal. This is going to be expressions that are equal. This is the sea of expressions.
Mm-hmm.
And then we're asking which expressions are equal. You know, basically this is the one we want. You know, quotes, which expressions are equal in the sea of possible expressions. Equal with respect to this axiom system. In the sea of all possible expressions. Okay, now that's unfortunately not yet a great model for math as such, because we find that this, but this is very interesting. And this is telling us, okay, so basically what this is saying is, if we can find a global model, then we can use this to figure out equalities that might later be proved. A valid global model, you can find this to guess equalities that might or might not later be proved by entailment, right?
Well, should we relate this to observer theory now?
How?
Well, I'm not sure, but obviously the observer has to come in.
Yeah, the observer has to decide. The observer is potentially making these models. Yeah, that's an interesting thought. So the observer might be making models that knit things together even when they are not entailed.
I suppose.
Yeah, that's what should be happening. I mean, and
That's a new idea. That's a new idea.
combines things which agree according to a model, even if they are not, in fact, entailed. So the observer might have the wrong model.
Sure.
Yes. If the observer, yeah, this is what's going to happen.
Yeah.
If the observer has the wrong model, this will somehow be discovered / shredded by the entailments. Okay, so let's look at the case where the observer, where was it? Where we had the model.
So does that mean that if you have something that's multicolored, the observer would be shredded?
Well, so in this case,
Yes.
the observer is going to combine
Mhm.
the observer is going to distinguish these two, even though they are entailed.
Right.
You know what I'm saying?
Yeah. Yeah. Oh.
So
Oh.
in other words, the observer is going to define certain patches. And those patches will not be the same patches that entailment defines.
Right. So this is different from the, see, there was this other error that we described before relating to rule viruses, right? Where you actually establish too many entailments that explode. But this is a different kind of error. This is that there actually is entailment that links statements, but you don't link them because you've assigned different models to them. Is that right? Is this a different kind of observer error?
Perhaps so. It would also be nice to see a rule virus blow up here.
Well, but the rule virus might blow up, but if it's multicolored, you wouldn't see it that way. Would you?
Well, the rule virus can only be multicolored if you have the wrong model.
That's what I'm saying.
Yeah, if you have the right model, the rule virus is like camouflage.
Yes, it's apparent in all its virulence, right? But if you have the wrong model, then you're not going to see all the entailments.
Yeah.
You're going to distinguish. So there are two kinds of, you can either assign too many or too few entailments in your fabric. This is new.
Yeah, it is new.
This is
And
new
it's
and
rather
intriguing.
interesting.
Yes.
Right. So, okay. So hold on. We need to do the accumulative case of this, right? Because what we've seen here is how by the way, we still didn't even start on the topic we were supposed to be talking about here. But anyway, never mind that. We did cover a bunch of model theory stuff, which is
Oh,
good.
you mean the MetaMath language?
I want to talk about that because I think it's not unrelated to this. Okay. So what we've got here. Okay, so we've got models here, and I want to look at. Okay, I'm still trying to wrap my brain around this. This is saying the observer picks a model that allows them to color all the expressions. That allows them to guess which expressions will be eventually entailed. If they pick the wrong model, they will claim that things are equal that aren't ultimately equal. Okay, if they pick the right model, okay, so they pick the wrong model. So according to the observer, they have made into an equivalence class everything which has the same value under the model.
That's
so
right.
that would be an observer puts in a single equivalence class everything with a particular value under a given model, under their chosen model. Okay, so now, entailment could show that items in the same observer equivalence class are not connected. right?
But what entailment? Observed entailment.
No, just entailment as you make the entailment. I mean, in other words, i.e., starting from the region of metamathematical space
Mhm.
defined by the observer's model,
Yeah.
there could be sort of tubes going to different places, as opposed to the there could be tubes going to different places, tubes going to different places in the sense that they go to different observer equivalence classes.
Good.
So the observer will see, we can make a picture of this. So the observer will see that their model was wrong. Okay, so what we should be able to show is there are a set of things that lead from a 48, for example. Yeah, this is easy. This is easy. I see how to do this. Okay. So what we're going to do is we're going to say, okay, so we want to make a list of expressions that start as quotes 48s. Okay.
Okay.
Then we're going to see where they go in successive steps. See what model they go to on successive steps. Okay. So if the observer has a correct model, nothing will ever go to a different.
You shouldn't call it model. It's like it's a value under this model.
No,
How do you call it?
no, it's a correct model. If the observer has a correct model, nothing will ever go to a value different from the one it started in. Right? That's what we saw. Okay, that's what we saw back way up here. Okay, in the correct models, everything that's entailed has the same value. Right, but in an incorrect model, this is what we'll see. This is what we should see. Hold on. Let's go down here. Each thing here has an entailment. So each initial condition goes to a bunch of values. Okay, so let's look at this. Okay, so we've got this here. Oh my gosh, my brain is beginning to fry here. Okay, I need help. I need help here.
Yes.
What we're trying to do is we're trying to look at, okay, I'm going to write down what we're going to do. We're going to take all start with a particular model.
Okay.
Take all initial expressions. and work out their values. Now look at what values those lead to in subsequent steps. Okay, so what that's going to be, if we simply make a graph of the value, we could make a value transition graph, okay, where the nodes are values.
Okay.
Well, i.e. are equivalence classes from the observer. We could also make this, it would be nicer to make this as a community graph plot. Do you see what I'm saying?
Yes.
And you know, as a community graph plot, we should either see all entailment connections being within a single community, or we should see hopping, right? So they could be that they're all involved in a single community, and they just circle around, but there are many communities. There could be many initial communities, but everything just hops around within its community. Or in a correct model, that's what should happen. Make sense?
Yes. Yes.
In an incorrect model, the things will hop from community to community. Okay, so let's take this, and what we're seeing here if we took this and instead of drawing a graph in which the nodes, in which these are just the labels of the nodes, we make the actual node value be this number. Do you get what I'm saying?
Yeah.
All right, so let's do that. Although we don't actually need the vertex delete anymore. We don't need the vertex delete stuff, I don't think. Because we're perfectly happy to just see the thing hop to a larger, well, okay, we can leave the vertex delete for now. So then instead of here saying vertex labels arrow this, what we want to do is a vertex replace, if I'm not mistaken. Does that seem right to you? Is there a vertex
Yeah.
replace?
Yes, there is.
But can we do that in parallel, all of them to the same, so that they're going to the same value?
Yeah.
Okay. Okay, so here what we want to say is vertex replace of G.
Well, I think it's not vertex replace. You kind of, so each, you still have the same nodes, right? But you
No, I don't.
connect
I
them.
want to look in the community plot. We want to move them around, but this is not the community plot. This is just conflating. This is putting all the zeros in on the same thing. We're going to have a great big flower of zeros going to zeros.
Okay.
Yes. Flowers indeed.
Okay, now notice that these transitions go between different values. Okay, so now let's use a correct model. Where is our correct model? Up here, 0, 0, 0, 1. And now I claim there will be no transitions. There will be pure flowers.
This is awesome.
Yeah, so now it blooms.
Look
They only have 3 flowers blooming, but so it goes. Okay. Okay, so let's review what we've got here. So what we've got is if the observer has the right model, then they will say all is good. What I thought was equal is equal.
Right.
If the observer has the wrong model, then they'll keep on seeing things kind of jump around. Okay, this is a pretty nice example, actually, because what we should see at the beginning here in the initial state is just a bunch of singletons. There'll be a bunch of dots labeled from 0 to whatever it is. 64, right? It's 2 to the 6. No, is it 2 to what is this number? Why is there a 48 there?
Well, that's how you derive the value from the expression after applying your model.
I see. And it probably goes up to 64 or something. Okay. Okay, fine. All right. So it will be interesting to see here as we scan over all possible models. Let's just see whether that works. I wonder if you can do it in parallel. I'm running all kinds of junk on my other machines. So let's just scan over the first few models.
Okay.
Let's say 5 models, and let's make this framed. And let's say labeled. And the way we're doing that is we're saying from digits, flatten comma 2. And that's wrong because this function needs to be outside all of that. And it's even more wrong because we need that taken out. And let's give this a, what the heck? Okay. All right, so what we should see here are some cases are correct models, at least as far as we're going here. And so their entailments lead back to the same values.
Okay, 0, 1, correct. 2, 3, 4 should be incorrect.
And that's what we see.
And then 5, if we had it, would be correct.
Okay.
Goody.
Yeah. So, okay, so this is the signature of okay. Okay. The question is, what is the accumulative analog of this? So so this is what we get for equivalences. Yeah, according to models. Okay, I understand this. This is good.
Mhm.
Okay, so now down here, what we're saying is we start from kind of the mathematical Big Bang here. This is a slightly different case. And what we're getting is things for which there are additional equivalences
Mhm.
not covered by the model.
That's right. Yes, that's right.
Okay. So now the question is, if we start from all possible
Okay.
Big Bangs,
Initial conditions. Yeah. Yep.
what we will get is more in all possible initial conditions, all possible initial axioms. Wait a minute. Okay, wait a minute. The analog of what we had before, the analog of the equalities-based setup is that a given that for a given model, that initially works, the values. No, that's nonsense. The model will just keep on working. Never mind. Okay, so the thing that we're trying to understand is our initial soup
Mhm.
will have a certain set of signatures here. So I think all we need to do is take this picture.
Apply it for all initial conditions.
Yeah, I think so.
Let's see if we can do it.
Well, and let's see what happens there, because what we'll want to see is for which let's see, we apply this for all initial conditions. Well, let's just try it. How do we get, I've had code that does this before. How do we enumerate possible ones of these?
Groupings of tuples.
Well, I know, but well, okay, all right, fine. And then we'll do a sort. Okay, let's just do the same thing we did here. Okay. So now we've got these, and we need to put blanks in them, don't we? Is that right? For what we're doing here? Yes, we need to put
Yeah.
blanks in these. And then we've got to look at all possible pairs of these, right?
Mhm.
Tuples, comma 2, and we've got to do a sort / at.
List. List of 2. Exactly 2.
That's what tuples does. I'm a tuples expert, he says, famous last words.
Yeah, right.
That's a lot of these guys. Do we want to get rid of ones which are the identity, or do we not care? Why do we care? Okay, let's do the case of 2 first of all, which is not going to get us to this thing here. But now what we can do here is this is just the exact same thing, but feeding in all of those inputs, right?
Should be.
Do we need canonicalized patterns, or do we not bother?
Mm,
Let's do canonicalized patterns here. So again,
then you need the union of that.
right? But does this work for canonicalized patterns? Okay, so there we go. Okay, and then union of this. Interesting. Okay, so let's take that and try this. Let's just go one step just to begin with. Oh gosh, why is this so slow?
Well,
Are you surprised?
Okay, why? Oh, I see. Those are different axiom systems. What the heck is going on here?
they're not necessarily on top, the axioms.
Well, maybe we need a layered digraph. What on earth is this? Okay, well, maybe we need to look.
Highlight the axioms at least.
Right, I mean, let's see what the vertex count is here. Ah. Oh, that has a bunch of events. Okay, so it's still much bigger than the number of axioms. Okay, so now let's look at the axioms. Here's the part I'm confused by. I would have expected this. Let's see, from a given axiom, the claim is things only fill in. Starting from a given axiom,
Well, it's weird because here you use all the axioms and they combine with each other.
so you're saying what we should instead do is make this and do a graph union of some kind.
Yeah.
This is a very weird object. This is not making a fabric. This is making some other kind of weird object. But let's highlight the axioms anyway. Okay. Do you know how to do a highlight graph? Will highlight graph work on this? Or will it?
Oh, it will highlight the dots.
Yeah, right. Highlight graph %153. And then let's go %151 style %151 comma red. I don't know. Can we do a point size here? No, we can't. Not sure what that will do. Is that the bug associated with patterns being?
Maybe. Yeah. It's not with the patterns, it's with the two-way rules, I think.
I can't see if there's red things there. Okay, let's do this. Let's take graph of %153, and then let's say vertex size, arrow, and then let's say hash arrow if member queue hash comma.
You already have the vertices. You just need to map them with the bigger number.
Okay, what do you think a bigger number is?
Oh, 1.
Where are the vertices?
Percent
151.
151.
I don't understand. Unless there's some pattern thing going on here. You know what I'm saying? I mean, unless these are matching, unless the point is that
verbatim or something.
okay, you think that will work? Let's try.
Around hash.
Better. I wish we could make them a different color. Do you know how to make them? Well,
Vertex style.
yeah,
Same
vertex
thing.
style are the same thing, right? Okay, there are our axioms. Okay, what on earth is going on in this picture?
It's like a piece of roulette.
Yes. Rulliad is a very wild creature.
You don't say.
Over. You know, what's disappointing about these things is if you take something like a quantum field theory, which is also a very wild creature, but it's 100 years old. you know, the amount known about it now relative to 100 years ago is not as dramatically different as one might hope. You know, one has things like perturbation theory and one has lattice gauge theories and things like that, but it's been a very slow process. And the ruling out is much wilder, but maybe the wildness will actually help because it's more explicit. And anyway, okay.
Yeah.
So this is this case. All right. So this is a somewhat incomprehensible thing. Okay. So let's do the other case, which is one step. This was only one step as well, but that was a very obscure thing. Okay. So let's do the one step version of this
Each axiom.
for each
Separately.
axiom. Right.
Yeah.
Okay, so how do we do that? So we want to do this. It's this thing basically mapped over that, right? And then we want to do a graph union of those. Am I right?
Mhm.
Okay. So this is map this. Is it worth keeping all the vertex labels or should we add them back in at the end?
Yeah, it's better. Well, it doesn't matter. Just leave them.
No, I think what we should do is this. Let's take this thing here and let's map this over axes. And let's now do a graph union at that guy, right?
Mhm.
And then that's that thing.
Mm,
What did we do wrong? Do we need a list around this? We might need a list there. Oh, there we go.
Mhm.
Okay, what's happening here? What the heck is happening here?
what is
So
going
first of
on?
all, there's only one connected component. What's that?
And there is no events. It's like, I don't know.
Well, but what happened to the events? Oh, because they didn't make it in the graph. No.
Oh, graph union. Yeah, right.
Okay, let's try 2 steps.
Graph union. So it's like the styles of the events not coming through the graph union.
Oh, right. Yes, so there are events here. Yes. Well, we could do that by saying in this, we could do vertex style arrow. And then can we not do a pattern here? Can we say underscore?
Like least event or except to a rule.
Yeah. Goes to yellow, let's say. Actually, we don't need that. We just need. Not our most beautiful event rendering, but I think it gets the basic point across.
Yes.
Okay. Okay, what this tells us is, what does this tell us? This tells us that I'm pretty confused by this picture. Can we prune out the events? Because do you have a function that just prunes the events and makes the multi-way graph based on the pruned events?
Or just remove events. Yeah.
What is it called? Remove events?
Yeah.
Oh,
Okay, what are we looking at here? What we're looking at, okay, each of these is a little entailment cone.
It should be covered.
colored by a single model? No.
No, a single event, a single axiom.
Yeah.
But you don't color by axiom. You color by model.
Well, but there are two different things you can color by. All right, let's zoom out for a second. What are we trying to get here? And I think I'm getting fried out from this issue. Let's see. What are we trying to do here? What we're trying to find out we have already understood okay, models in this accumulative case. Where anything entailed has more models, right? Anything that is successfully entailed by something has more models. But what we've got here is something where there's a kind of a, in the end, let's see, we start off with things which have a variety. Okay, let's do this. Let's do this. Let's just take our original list of axioms and ask what their model signatures are.
Great.
Okay.
Yeah, that's concrete.
Okay, so now the model signature is that piece. Okay, so we can just map that over, instead of find finite models, no, it's actually just exactly this. Just this mapped over this thing here. Okay, there we go.
Okay. A
Okay, so
goes
not
to B has the
surprising,
same model.
not
as A goes
surprisingly,
to
AA goes to BA has the same model as AB
Yeah.
goes to BB.
B. A goes to B has the same model as A goes to A.
Let's think about that for a second. Well, A goes to A is simply true. So that's being filled in as the true model.
Yeah. Okay. What about A goes to B?
That has to be a false.
Yeah.
Yeah,
We
that's
don't
wrong.
distinguish.
We got
Yeah,
this wrong.
exactly.
We got this wrong. So, yeah, we got this wrong. Error, mistake. So we'll have to go back and fix that in all the other ones. False should be all white.
Ding ding. Right.
Okay, so we got to go back and fix that mistake. But not right this second. A goes to BB. Is that true or is that false?
Look, if A goes to B is false, why would A goes to B be anything else?
It's missing your operator altogether. So in both cases,
What's wrong is
it's
just this is
missing
wrong.
filter.
This is slightly wrong. We need to fix this. This test is not quite right. This, if it's equal to a blank there, we should have tested that for blankness. Yeah, this isn't right. That test for blankness should be further inside. Okay, because it's actually at the point where at this point, look, the problem is we're not distinguishing between, there are no models that involve a small circle and the models that involve something else. See what I'm saying?
Ah, okay.
All right, but so we made a mistake here, but never mind. Let's just ask the question, as we go down the entailment, I think it must always allow more and more models.
In the accumulative case.
In the accumulative case, yes.
Accumulative case.
That's what I think. And we could test that by not doing the graph union here. Okay, it'd be really nice to fix this bug. Can you see, Nick or anybody else, can you see how to do that?
Just don't use axioms without small circles. Doesn't make sense to use them anyway.
All right. Okay, fine. Okay. All right, here. So here what we want to do I want to say with G equals token event graph hash, not this, and that whole thing slash at drop AXS, comma 2.
Yeah.
Okay, well, this is kind of as expected.
Interesting. Yes.
It's just making more. Okay, let's live a little bit more dangerously. Let's do the 2 case.
It might be more dangerous than you think.
That's okay.
Yeah. I mean, we've got a few cases we got to deal with because we haven't dealt with the false.
Oh, it's not that bad. Okay.
Not that bad, no.
Oh, these are kind of fun.
They're nice. They're very nice. So this is showing for a given axiom system how the number of models. I'm not sure I believe this thing here, but maybe it's right.
Yeah, because you still can reduce to a token without small circle. So not really solves the problem, but
No, I
anyone
understand that,
else-
but do you think that's a tautology there?
the problem is that it can be either A equals A or A equals B.
Mm-mm.
No, I realize that.
Yeah.
Can anyone explain this case of
Sure.
A dot B goes to B dot A?
Where is it?
Yeah, that one.
Yeah, that's just giving.
Well, you can mute it and make a identity.
Yeah, for which it's trivially true. If A is the same as B, then A dot B is trivially the same as B dot A. And that's what we're seeing here.
Ah. Okay. Okay.
Okay, so what we're seeing.
Yes, I understand.
Okay, so what do we learn from this? What we learn from this is that if you say, I know what's going to be entailed, you say, I know what's going to be entailed because I can see what has such and such a model signature. And I know that something couldn't be entailed. Like, for example, I know that that guy there couldn't be entailed here, ever.
Does that mean that there's computational reducibility under model signature?
I think not, because I think what's got to happen is that you've got to be able to globally. I think what it is models involve a pre-computation of what's going on. But I don't quite know how that works in this case. So
what does that mean? It means it might seem reducible, but it's because you've already done the computation. Is that what you mean?
yeah, that's what I mean. I
Yeah.
mean, if you are trying to figure out what's going to happen in this entailment cone after a long time,
Yeah.
well, yes, you could just go and pick up all expressions in the what the heck do we call it? In the Roolead, basically. All expressions in the Roolead and go and check them. And given that you've done that, you've just lost the game. You're way out in sort of crazy computation land. But I don't quite know what this means for entailment fabrics. Entailment fabric is where there's overlap between these entailment cones. And I think the
Yeah,
models have to
that's
tell you
right, exactly.
where that overlap could occur.
That was my suggestion earlier on. So does this mean you basically are color matching these cones into a fabric?
Yes,
Yeah,
that's what you're doing.
yeah, that's what I think too.
Right. And I mean, you could, and that might over compute it. That might give you more matching than is right.
And when
Because the
those
expression might not be the same. It just might be that its expression signature, I mean, that its model signature is the same.
Okay, so what's the consequence of that? Let's say you match some cones together by color. Color's the same, but the expressions aren't the same. What kind of problems could you encounter if you don't do that right? As an observer.
Hold on 1 second, just 1 second. Um, I'm sorry, I'm just checking out something else here. Excuse me. Okay, sorry, let's refocus here. Sorry, I got distracted for a second.
Okay, so you're matching these cones together by color in a fabric. You're suggesting that it might be the case that they match color-wise or model-wise, but they're not exactly the same. They're not the same expression. But what are the consequences for that in the fabric? Should we consider an example, maybe?
Yeah,
Should we
well,
try and build a fabric?
Yeah, we could try to do that, but I think it's going to look messy.
What about a simple one?
Well, actually, what we can do is we'll build one from these where each one of these is a different color. Okay, where each one of these.
Are they all might some of them be the same color?
No. But I meant that we're gonna match these up. What's tricky is we got to show, in order to see what's what, we have to say this cone is knitted together with this cone, right? And this cone has to have a characteristic color, and that cone has to have a characteristic color.
In order
That's
to
what
be
we
able
did
to,
before,
yeah.
in order to be able to see what's going on.
With the
Otherwise
festivals,
look
right?
like,
Yep.
yes, that's what happened. Right. But the thing is, okay, so we've got festival matching, so to speak, which is as in each cone has its own color.
Fine.
And then we've also got the colors from the model signatures.
Yeah.
Okay, let's look at the analog of what we did before. Okay, so that what we did before, the thing about it is, in this case, there is a kind of an energy function. We are progressively generating the model signature is non-decreasing. See what I'm saying?
Yeah. In the cumulative case.
Yeah, effectively, there is an energy function, non-decreasing model signature.
But that's basically due to the accumulative property.
Yeah, it's due to the transitive closure-like accumulativity.
This is important. Yeah.
Okay.
Yeah.
So, okay, so given that, at some point you'll run out of information. Like when these just turn black, you lose all the information because they're all the same.
Is that a
So what that means is that you have, I think it means the theorems you've proved are kind of trivial.
does it
And
mean
it's
it's
true for all.
reducible? Does it mean it's reducible?
Possibly.
If they're all black, is it, no pun intended, basically a black hole?
Oh, let's see.
Because I don't see where you can go from there if they're all black.
No, I think those theorems are all trivial, but they may not.
Black is okay.
What's that?
Black is okay. It's true, right?
Say that again.
Black is okay. Oh, everything is black. It's just a true statement.
Yeah, it's a tautology.
Yeah.
But I think it tells you nothing. Once you have a tautology, can you wait a minute? Yeah, right. Once you have a tautology, I don't really understand this picture, and I'm suspicious that something, because there should be a sequencing here. Wait a minute. These things are ultimately always two-way. So how come that would imply that something could not follow this energy function?
What?
No, you see what I'm saying? If how can this graph be two-way? Nick, is this graph two-way?
Oh. Not necessarily.
I didn't presume that it was. I presumed
Because
that.
Okay. If it is two-way, then if it's two-way, the things must actually be equal. The things must be model equal. The model signatures must be the same if there's a two-way link.
But that would be really confusing.
But it's true. Look at this one here. You can see it. See that one there? That one goes back to there, and it has to be the same in that case.
Yeah.
I see. You can take a little loop from that one to the one above,
right.
back through different events. Yeah.
If there is a loop, everything has to be
That's nice.
has to have the same model signature.
So you can contract that loop down to okay, I see. Yep.
Well, let me see here. So Well, I'm still not quite clear on what. I mean, we've imagined that a model defines kind of a reference frame. And in this case, if we had this notion that the model gradually, that there's a sort of an energy function, that's like the time function, that successive layers that we can define space-like hypersurfaces. I don't know if it's true, but it must be true. Yeah, it must be true that we can define space-like hypersurfaces by virtue of the fact that they have to be gradually increasing. Things are time-like separated.
Oh my goodness. Does this mean that even if we have a framework, a meta-mathematical framework in which overall it's atemporal, the observer will experience time because of the accumulation of models?
No, it's kind of like math progresses.
For the observer. Yeah.
Yeah.
That's very nice.
Things are time-like separated when they have quotes increasing model signatures. Yeah, so that's an emergence. Well, it's a little weird because we're saying there are more models. Usually, like a typical sort of weak model is abstract group theory. And you add more models as you actually give sort of relations in the group.
Yes, sure.
So the question here is, as you give more relations in the group, more things become true.
Sure.
I am confused here because what I would think is that there's a sort of a big bang that starts with abstract group theory. Is it the case then that within the big bang of abstract group theory, there are particular groups that exist on different branches of this accumulative token event graph thing?
Interesting.
I don't quite understand how that works because those are particular cases. This is normally our entailment, our laws of entailment say it's got to be globally true. Does it follow? I'm confused, and I think it relates also to Skolemization and existential quantifiers. I think we've probably expired our time here.
Well, what has this been, a 4-hour stream?
Yeah, something like that.
Well, it's been fruitful.
We're making progress. This is good.
Very interesting
Okay,
stuff.
so I just want to have a quick question. Okay, it's like famous. Just one more thing.
It's not about MetaMath though, is it?
The MetaMath database.
Yeah.
Well, it is, because I just want to ask, given what we've seen here, what did we how far did we get to? We got this was our attempt, which actually wasn't about MetaMath, to ask the question of as we explore Boolean algebra. Yeah, okay. So this was about theorem proving, but I'd even forgotten we've done this now. Yeah, so what we wanted was directed entailments, directed sort of theorem search, directed theorem enumeration. That's what we want is the final thing is directed theorem enumeration. In other words, instead of making the whole cone,
Right.
we only want interesting theorems. Okay, the question is, where are those? And so what we're saying is, in MetaMath, what are we seeing? What we're seeing is, we're seeing a skeleton, okay, in the MetaMath database. We're seeing a skeleton of the entailment cone, I claim. You see what I'm saying? Nikki, if you're still awake,
Yeah.
Okay, so that, because in other words, what we're seeing is we've got particular proofs of particular theorems, just like up here, we saw way at the beginning. Was it here or was it in the other one? No, I think it was here. We're seeing that the theorem prover gives us a particular path. Okay, we're making two choices. Right? We are making the choice. Yeah, this is our example, right? There were three proofs, and okay, so there are three proofs here. ATP found one. There are many theorems. You pick the one you want. Okay, so what MetaMath is, the MetaMath database is doing is imagine the entailment cone for all of mathematics.
Okay.
Okay, imagine the entailment cone. Okay, MetaMath database. Imagine the entailment cone from the axioms of set theory. The database has a very thin skeleton.
Sure. Compared to that.
Of that
course.
entailment cone. Okay, so the question is, what would we learn by drawing that skeleton? Because what we're seeing above here is that the skeleton is incredibly thin and gangly, right? It's got 700 step things to the theorems of interest. See what I'm saying?
Mm-hmm.
So, and let's even give the automated theorem, let's even give MetaMath the benefit of the doubt that its theorems, that its proofs are minimal.
Okay. Nick, you think that's valid though?
I don't think it's valid, but I think it's a
No.
good approximation.
Fine.
Let's, for the sake of argument, let's assume MM's proofs are minimal. Okay, so then what they are is from the Big Bang, they are, you know, they are individual paths. Well, okay, they will have some it's a skeleton, basically.
What has to be?
Yeah, it's a tiny skeleton, but the only question is, what do we learn? So for example, okay, e.g., can we estimate whether the skeleton is uniform across the entailment cone?
What would it mean for it to be uniform?
That Well, let me give an example of that. Okay, so let's say we have a grid graph. Okay, and now so we're going to make a skeleton on the grid graph. Okay, starting from, let's say, that node. I don't know how to do this in a picture. Right, so we're going to ask whether the things that end up, whether the places we end up are uniformly distributed in the entailment cone.
Oh, I see. Okay.
I mean, I have no idea. That's a question of how well mathematics has been,
Surveyed. Yeah, right.
Yeah, right. Is it, I mean, my guess is probably not very uniform in the entailment cone. And instead, what's happened is,
Well, sure. Yeah.
Guess is it's not uniform in the entailment cone, but instead it's built out in towers.
Yeah, and the question is whether or not those towers correspond to parts that are the most easily surveyed, or if even human
That is the
institution
start.
building has played some role in that.
Right. Is there something special
Right. It could not be. There could be
about the towers?
There could be basically sites where towers could have been built and could be built, but they're just not there because we haven't done it.
Yeah, but the big point, okay?
Drum roll. Yeah.
Yes.
Yeah.
Is that higher level math is possible. Therefore, having a sparse collection of towers is, quotes, enough, maybe enough. Okay, so in other words, the whole entailment cone, i.e., you can talk about math without going through all the detail of the whole entailment cone. Right? Because that's the point, that we believe that there are these higher level constructs in math.
So hold on.
So in other words, yeah.
So if higher level math is possible, this basically means that motion in metamathematical space is possible. So the point here is that you can only have a sparse collection of towers, but you can still move between them, and that motion should be able to actually cover.
Well, another way to put it
is
important. Another way to put it is that around every the sort of the balls around every statement in the MetaMath database,
right,
are big enough in entailment space, so to speak, or in emic space somehow, ultimately are big enough that, because the claim is you can have a grand old time just going between those things without having to worry about the fact that as you move from one to another, you are, transforming into all this weird emic, very low level stuff. You can talk about things just at this high level.
Yep.
And so what that's saying is that it's enough to cover the entailment cone with patches and it's somehow possible to go from one patch to another. Right. This is the possibility of motion, basically.
Well, right. That's what I was trying to say. Yeah. So long as
Although motion in entailment fabric is a little bit unclear what the heck that means, because it's basically saying, I mean, motion requires an idea of time. Which is all right. I mean, there is an idea of time. It's just that it isn't the instantaneous fabric.
Well, but our new idea of time is basically the accumulation of these new models, which is basically the generation of new equivalence classes. No?
Yeah. I'm not sure if that's quite right, but the main thing is that okay, so what can we learn empirically from the MetaMath database? We'll be able to construct, it will be nice to see its skeleton of the entailment cone. Nick, are we able to produce that?
No. No.
Nick never says no. So.
Yeah, that's a bad sign. Okay, tell me why not. In other words, every theorem is a node. Why can't we produce pictures that are like our token event graphs?
We can. I guess, yeah, we can.
Okay, so that's what we'd need. I mean, and it has whatever. And okay, so
It's going to be more complicated because the token event graph is going to have more than 2 inputs in general.
Why?
But they're going to be much simpler because substitution in MetaMath is kind of multi-input one. It takes multiple inputs. Each event of substitution takes multiple inputs.
Okay. The substitution entailment is more complicated.
But it's in the same sense easier because it's only the substitution, meaning you just replace the variables, not just some arbitrary sub expression.
I see, but it's a simpler. That's not something we should consider in general, is it? That form of substitution.
Then you just replace the variables.
Yeah.
Well, in some sense, that's what we also do, because substitution is when you just do replacement of variables. It's just when we do it, we first have to pick where we have to do it. It's like all our rules just match sub expression to some expression, and then there's like substitution of variables is going on.
You're saying MetaMath, yeah. But you're saying MetaMath has only the substitution of variables without matching the subterms.
Oh, I think so, yeah. Yeah.
We should understand what that is. I'd like to understand what that is and how whether that is relevant to everything else we're doing. But okay, so then what are definitions in the MetaMath database? What do they correspond to?
Oh, just like lemmas, theorems.
Where we introduce a new operator, right? Definitions are something where we're going to introduce a new operator, aren't they?
Yeah, a new function symbol.
Yeah, each definition introduces a function symbol, which when we fish it out of Eames, so to speak, is, I mean, we imagine that there's something lower level than that, but that's not what MetaMath is dealing with. But so we should be able to make the token event graph. I thought you had done something like this before, Nick.
Well, yeah, I had a graph, more like a multi-way graph, not a token event graph.
Okay, fine. That's good enough. So what was in the multi-way graph? It was theorem. What was in the multi-way graph?
Just theorems from the MetaMath database. And its arguments, like variables, also it's like can be a vertex there. Variable, basically terms. Yeah, expressions.
Where do you have that? Let's take a very quick look and then we should wrap up.
Well, MetaMath proof,
In
not
what?
ready. Not ready functions.
Oh, okay. Oh, you just edited that today because you were getting ready for what we said we're going to talk about in this meeting. Thank you.
I haven't done much with this. I don't know. Just look at it. Press save again.
Okay, what are these pictures? So that picture, what is something like this?
The tree is just well, how to call it? Well, basically a proof. It's a proof of some theorem. Where each
Using
node,
what?
using
Yeah.
axioms or lemmas. Depends how you expand it. I think this tree is expanded to only to have axioms of the database.
So how do I read this tree? Is this the theorem being proved?
No, I think it's the last lemma that then produces the theorem that you're proving. So this is, I think, the last one is some kind of equational transitivity. So it takes as an argument a bunch of other statements, like some one equality and another equality, and some variables.
So we read, so time is going up the page.
Right. Yeah. It's like a proof graph upside down.
Okay, and what are these things at the bottom?
This would be variables, not the duplicated.
Is this the proof of my Boolean algebra axiom? Because if it is, it's probably not the most interesting one, because it's not really a human-made proof.
Well, some of them. Well, there is a human-made proof, right, of your Boolean axioms.
No, there isn't. No, there isn't. The Norm was working on making it more human, but he's got a long way to go.
Well, yeah, but still, he made it shorter. So.
Yeah, I know, but he made shorter a thing that was utterly incomprehensible before, and he made just have nipped and tucked it. Not, I think we shouldn't look at that for a comprehensible case. We should look at one of the more straightforward things. But so what you're saying is that I'm confused by something. Why are there many copies of one theorem here? Because in our graphs, there's just one copy of each theorem.
Yeah, but if you deduplicate this tree, it's basically what the graphs are showing you there. It's just these three.
I see. So the tree is what is in the explicit thing, and then the graphs of the deduplicated tree that show how you evolve from certain axioms. So what you've got is the skeleton of a token event graph. Yeah, I mean, you've got exactly what we would expect. It's the same kind of thing that you've got in your theorem proving token event graphs. That is, you've got certain axioms, it bushes out a bit, but it fundamentally only follows one path to get to the theorem.
Right.
But because we have a multi-destination thing, because we have multiple theorems, we have whatever it is, 20,000 theorems in the database, it's a multi-objective theorem proving. And so there will be crosstalk between those multi-objectives. If we only had one theorem we were trying to prove, like in this Boolean algebra case, then the thing will look just like your automated theorem proving token event graphs. But because we have many, they will have crosstalk between them and they will fill in some of that structure. Okay, so we need to see that structure because that structure is either laid out on the entailment graph kind of I kind of think it's going to be yeah, our claim is, okay, so one thing about how one does math. Yeah, the whole point is this. You're dealing with things that are at level of big theorems. You are embedding those in the entailment graph, in the entailment cone, entailment graph, which is an incredibly low-level thing. And the fact is, most of the time, to get from one place to another, you do not even need to look at the entailment graph because you can operate at a higher level. Most of the time, okay, so what's happening is, you know, MM is embedding all math in an explicit entailment graph. But most mathematical conclusions, aka mathematical motion, never has to look down to the axiom slash eames slash whatever you call them. Right? You can do motion, just like in physics, we do not have to look at the atoms of space to understand how to do motion. We have laws of motion, e.g. in physics, we have laws of motion that don't talk about the atoms of space.
Well, none of them do.
Well, except the ones in our project.
No, but in physics with a, yeah.
With physics written in some kind of calligraphic font of the past. Pre-modern physics. Oh no, they're going to have to. Would it be shocking if somebody one day has to? What on earth will they call modern physics when it's no longer the modern physics?
Well, they'll have historiographical paradigms, which we ourselves are already starting to apply.
Well, no, it's interesting. So it's modern physics is physics that came after 1900.
Yes. Well, perhaps people won't use the term modern to mean contemporaneous at some point, or sorry, contemporary.
Perhaps. It reminds me of one of my favorite naming glitches, which is New College in Oxford. It's the second oldest college at the university from 12 something or other. But it was new relative to the first college. I also was very taken with the fact that, you know, a long time ago, and I was like 10 years old, when the currency decimalized in England.
Yes.
And I don't know whether they still have it on the coins, whether it says new pence. I wonder whether they ever took that off. I have to look. Okay, in any case, basic point is, in physics, we have laws of motion that don't talk about the atoms of space. In mathematics, we have ways of doing mathematics that don't go all the way down to the axioms. That is our, you know, analog in math is human level proofs, which don't go down all the way to the axioms. And that's what most current math is, unless it's done with proof assistance. And the problem is, as we're seeing here, that because there's nothing, the concept that you summarize your math by giving axioms is ultimately not the right concept. Because ultimately, there are no, quotes, correct axioms. There are only axioms that are or not consistent with sort of human observer qualities.
Well, sure. That's a key assertion of this entire project, which you can understand when you take a fourth paradigm view.
Right. It's also what Euclid did. I mean, not to feel too modern about it. Because basically Euclid said, I'm going to write down these axioms which are consistent with our human experience of the world.
Yes. True. Okay.
So we came full circle. It's just Hilbert and Whitehead and Russell were kind of out in the wrong direction. Because what Euclid was doing was exactly what we are talking about doing. That is, trying to make axioms that are sort of human appropriate axioms, trying to summarize mathematics. Picking not arbitrary axioms, but axioms that are sort of human-like.
Well, right. But the challenge is you can do that to a certain extent due to what you can observe naturally as a physical observer, which I would say with geometry, that's what Euclid could do. The greater challenge is...
Yeah, it's less obvious how it works
yeah.
in set theory, for example. But
at some point you need computers, basically, at some point. Here we are.
Yeah, well, we can tell. I mean, honestly, looking at any of these pictures, we can kind of tell that we need computers. I did lay out graphs by hand back in the day. Then I found this young woman who was really good at detangling graphs for the NKS book. She did the ones for that before we could do it automatically. Okay. Well, we should wrap up here. We've gone way longer than expected, but this was productive, and we've got some cleaning up to do here. But I think this is good, and I think what we understand about the MetaMath thing, I think it would be nice to try and draw this graph.
Mm-hmm.
I don't know what the significance of the graph I already drew. I already have these graphs like these ones here that show these different areas. I think those are, show what refers to what in different areas.
Right.
What the heck are those graphs? This is some thin skeleton of the entailment cone asking it'd be nice to see what's inside those things, because we know that this is a way of kind of coarse graining. This is an ultimate coarse graining, basically.
Well, for now.
Yeah. So that's kind of extreme coarse graining. Where the main thing you learn Right. Well, you're no longer talking about individual mathematical results. Just as in a mathematical result, you're not necessarily talking about a specific axiomatic result,
Mhm,
and you're not talking about a specific emic result either.
mhm. No.
Um, okay. Well, we were also considering doing this thing with the math genealogy database, of looking at that's a thing where it's a flow through time. I mean, the bibliometrics or something, or the studentometrics of mathematics, so to speak.
It's still not exactly clear to me what kind of time that is, though. We had discussed that, then we began to question our assumptions regarding time in the metamathematical framework. And then we didn't really revisit it after that.
No, I agree. And I mean, I think that the time is roughly, look, the entailment fabric is the state of mathematics, is what is there in mathematics. Now, we humans, it's like saying, it's like what we do in physics, where space, there's one process, which is the creation of space, which is a giant entailment cone, basically, that started at the beginning of the universe. Then there's the question of us wandering around in space and exploring more of it,
Mhm.
which is a time-based thing. You know,
Yes.
and we can, yeah, I mean, that's something where, you know, space and mathematics are created in some sense timelessly. I mean, space is, there's a notion of time in the creation of space. There's a notion of time in the entailment cone. But we can also imagine that we're exploring how mathematics is put together
Yes.
without seeing it from the Big Bang. We're just looking at it. We're just, you know, we're exploring the current state of mathematical space. But we do that, again, through time. So, I mean, it's again, rather than all of the entailments that are creating the mathematical space,
Sure.
we are following specific entailments that that allow us to go from this place to that place, I think.
Sure. Yes.
And so what's happening is the space of mathematicians, you know, mathematicians live in mathematical space in some sense, and they are wandering around and generating students that are in different places in mathematical space. It's kind of cute. It's kind of natural selection. You know, we've got this trait space. We've got some, you know, the space of we've got mathematical space of possible mathematicians, so of possible math.
Mhm.
And then we're saying that any given mathematician can have some sub-mathematicians, so to speak, that are generated, and that gradually, I mean, that's another. Yeah, okay.
It's like a covering of metamathematical space.
Yes, but I mean, wouldn't it be ironic if we managed to figure out something about a model of evolutionary biology by studying, because I mean, this is a slightly more, okay, the trait space of organisms in biology is probably even wilder than the trait space of mathematicians in mathematical space.
Oh, probably.
Right. So, I mean, what we're saying
Probably.
is if we look at how mathematicians generate progeny in effect, I mean, it's a little bit weird and different in terms of I'm trying to think what the natural selection. I mean, the natural selection thing is some fields. Yeah, I mean, you have all kinds of things. You have many mathematicians in one area causing this and that and the other. And
Well, I had a different view, which is we discussed this notion of proof fitness at one point, or the you see, I wonder if it's you have mathematical genealogy as a cover space, and it's basically reflecting what can be studied metamathematically, and it's the proofness or the fitness of, how should I put this? I'm a little tired.
okay, we should wrap up. I need to get something to eat.
Yes, likewise.
Okay. All right. Well, good work. Thank you very much. And thanks to our folks on the live stream.
Yes.
And we probably won't be doing another live stream. I don't know when we'll be doing that next live stream. We might even have one about a different topic tomorrow. Yes, we do. And if we can survive it, we could actually continue this, and we could even perhaps live stream it sometime tomorrow. Anyway, we'll talk about that separately. Okay.